Have you ever lay down in bed before going to sleep, then suddenly out of nowhere thinking, what would the world be like in the future? Followed by an existential crisis?
That's me. But no worries. Today I'll be discussing a theory in the field of cosmology, the expanding spacetime theory. But before we start talking about the future, let's head back to the past. When Einstein published special relativity in 1905, then general relativity in 1916, Russian cosmologist Alexander Friedmann was inspired and came up with the expanding spacetime theory under the paradigm of relativity, solving Einstein's field equations. Friedmann theorized his model under two standards, the Big Bang theory and the steady-state theory. But the steady-state theory was then tossed out after the discovery of CMB, cosmic microwave background, in 1965. Is that enough for the background check? Let's head back to the future. Let's start with the basics before we go further. What is spacetime? Spacetime is a concept where time and space, temporal and spatial, are fused together, creating a four-dimensional continuum. But we might think that time and space are totally different things and they're separate. But actually, they're not. Let me show you. Let's head back to my room. Over here is the spacetime model. Space is the x-axis and time is the y-axis. Pretend that this little figurine is me. I'm here right now. If I'm standing still for an amount of time, the graph goes up as time ticks but my space doesn't change. But what if I walked? See how I'm moving, making both changes in space and time because I'm moving in space as time ticks. So now let's start with the EST model because we already know what space-time is. So the EST model has two postulates. The first postulate is that space-time equivalence applies. Here's the keyword, symmetry. In the EST model, the world is expanding in scale as well as time. Supported by Hubble's redshifting discovery that galaxies are moving further apart in a constant rate, time should expand as well, growing slower. Imagine, this is the size of our solar system today, but in the future, it might look like this. As planetary bodies, we move further from the sun, and our orbital period will be longer in distance. Without the EST model, it would imply that the Earth would take less time to complete an orbit. But with the EST theory, the time for Earth to complete an orbit will remain the same because time stretches along as well as space. The second postulate is that all measured speed of light is constant relative to the observers. You see, all freely moving particles that are slower than the speed of light will decrease over time. Any moving particles that move at the same rate as the speed of light and light itself will remain as a constant and will not decrease over time.
This means the calculation of distances using the speed of light, for example measuring stars, will remain the same.
The EST model also points out that this second right now relates to the seconds before and the future. Here's a SLinky. Pretend this is time. A second right now could be this long, but in the future it could be this long.
As time progresses, each second grows bigger each time at the same rate. We call it an exponential or geometric expansion.
But here's the big question. Is the EST model even true? It's not 100% verified and there are still some doubts. But here are some evidences that support this theory. The first one is cosmic drag. Cosmic drag is when particles gradually move away from each other as spacetime expands and lose their kinetic energy, like positive mass particles decreasing in velocity and photons redshifting. Also known as cosmic scatter, it is easily calculated using Hubble's law. The formula is v, recessional velocity, is equal to Hubble's constant times distance.
As you can see, Hubble's data lacked, which concluded a very different result of the Hubble constant rather than NASA and Planck mission's current study on the true Hubble constant.
With these particles gradually moving away, this gives evidence to the reason why galaxies are formed in a spiral shape. Particles in the radius near the core will have much more kinetic energy than the ones further away, making the ones closer move faster, then followed gradually by the ones further. Stars further then have lower angular momentum, causing them to spiral towards the center. Another evidence is the activity of our satellite, the Moon.
The Moon goes further away from Earth at about 3.8 centimeters a year, calculated with the Lunar Laser Ranging Equipment tested annually.
The last one is that the rate of expansion has been calculated. Thanks to NASA's Spitzer Space Telescope, our universe expands at a rate of 74.3 plus or minus 2.1 kilometers per second per megaparsec. A megaparsec is roughly 3 million light years. Overall, I think this theory should be put into huge consideration and be studied further, because clearly there are many supporting evidences that put this theory closer to an approval. Anyway, thanks for sticking around. See you next time. So expansion is real. It is real, it is real, it is real.